Hello, my wonderful friends of Easy Maths Tutor. How you doing? Hi. It's been a long while. I've been in the oven, in the cooking room, cooking up myself and learning some new things to add more value to what we're learning. So today I'm going to solve a quick question about fluid dynamics that has to do with flow of fluid between two parallel plates. One of the plates, the upper plate is going to be moving and the lower plate is going to be fixed. And this flow has some of the following properties. We are going to determine the velocity and pressure distribution in a steady, fully developed laminar motion of an incompressible fluid of uniform viscosity between two horizontal infinitely large parallel plates, where the lower plate is fixed and the upper plate moves with velocity uo in the x direction, and the distance between the plates remains constant at h. So sit back and watch as I solve this. So this is what the diagram looks like. I have two plates of a certain thickness. Now the upper plate is moving, while the lower plate is fixed. And then we have a fluid flowing through in between these two plates. Okay. Then we have a distance between the plates, h. And then we have the directions and the y-axis and then the x-axis. Please let's note that the z-axis is coming towards perpendicular to our direction. Okay. And then we have a force of gravity acting on this. So the conditions of this flow as follows. Now for steady flow, partial derivative over partial derivative t is 0. Then for incompressible flow, the density rho is constant. For infinitely large plates, partial all over partial derivative in direction of z is 0. Okay. Now since this flow is in one dimension, that means it's moving only in the x-axis. We say a one-dimensional flow. And the plates are moving in x direction. We say plates. Therefore, the velocity in the y direction is 0. The velocity in the z direction is also 0. Now let's recall continuity equation. Okay. It's like this: partial ux all over partial x plus partial u in the y direction all over partial y plus partial u in the z direction all over partial z equal to 0. Okay, so for these conditions given, remember it's one directional, it's moving only in the x direction, so this will tend to 0 and this will tend to 0. Therefore, the partial derivative of the x component of flow with respect to partial derivative of x is equal to 0. So now we're going to apply Navier-Stokes equation. Apply Navier-Stokes equation for rectangular coordinates now in the x direction. For the x component, we'll use this equation. That's the equation. Rho derivative of u in the x direction with respect to t will give us negative partial derivative of density with respect to x plus mu. Okay, so we'll say partial ux all over partial x plus partial square uy all over partial x. Sorry, it's partial ux plus partial square ux with respect to the z direction plus rho function with respect to x direction. So if we look at all the conditions, all this will become 0. This will become 0. This will become 0. Okay, so this will also be 0. So our equation will reduce to 0 equal to negative partial rho all over partial x plus mu the square u the y square. Please, this is square. So this is our equation for our x components. We call it equation 1. So Navier-Stokes equation in the y direction is given by rho du, rho the derivative of u in the y direction with respect to t minus equal to minus partial derivative, partial square derivative of u in the y direction, partial x square plus partial square u in the still y direction is partial y square plus partial square u in the y direction all over partial z square plus rho f of y direction. All this will turn to 0. This will also turn to 0, giving us 0 equal to partial p all over partial y plus rho f of y. That is partial p all over partial y plus rho f of y will be our gravity. Okay, so this gives us our, remember there is minus here. Okay, so this gives us our second equation derived from Navier-Stokes. Now for the z component will give us what? 0. So from our equation 1 gave us 0 equal to negative partial p all over partial x. So minus partial p all over partial x plus mu partial square u in the x direction all over partial y square. And so we're going to integrate. We're going to integrate twice, okay? Well, first of all, we'll rearrange this equation. We'll have dp dx equal to mu the square ux all over the y square. So if we rearrange this equation to make the square ux all over the y square subject of the formula, we'll have the square ux all over the y square equal to, u will go under, so it will be 1 over mu dp partial p partial x. So integrating this function, okay, integrate this function. If we integrate it with respect to y, our answer will be both sides, okay, to be the ux all over the y, this is x, equal to 1 over mu the p partial x y plus our constant c1. Okay, so further integrating this equation, we'll have something like this, okay? If you integrate this will give you ux, and this will give us, integrating y will give us y square all over 2, okay? And we'll take this as the coefficients. So we'll have 1 all over mu partial p partial x y square all over 2 plus c1y plus a new constant, okay? So we'll write it out properly. We'll have ux after integrating twice gives us 1 over mu partial p partial x y square all over 2 plus c1y plus c2. Call this equation 3. So applying boundary conditions, at y, when y is equal to 0, ux will be equal to 0, and c2 will be equal to 0. So if we add all this into the equations, that's the first, the lower boundary condition, then also the upper boundary condition, when y is equal to h, ux will be equal to uo. So applying all this into the equation, we'll say uo is equal to 1 over mu partial p partial x. This becomes h square all over 2 plus c1 h plus c2 0. Okay, So we'll make C1 for the subject of the formula. If C1 becomes subject of the formula, what do we have? First of all, we'll divide through by h, okay? Divide through this equation by h. So we'll have h, we'll have h, we'll have h. This will cancel this, this will cancel this, okay? So making C1 subject of the formula, we'll have UO all over h equal minus 1 over mu partial p partial x dot h all over 2. So this is our C1. So we're going to put this C1 expression into equation 2. We'll put it here, C2, C1. This function will fit into this function directly, okay? So when it fits into this function, C2 will fit in as 0. And then I will get our final expression. So quickly, we're going to switch over to my notes and see how we solved it because of time and space. So if we put C1, this is C1 expression, we substitute C1 into equation 3 as I explained earlier. This is what we'll have. U 1 over mu partial p all over partial x y square all over 2 plus, this is the C function, okay? So there's something common in this function, and that is mu 1 over 2 mu and y. 1 over 2 mu and y. But we're going to just pull out 1 over 2, okay? First of all, we'll expand this, giving us UOYH plus 1 over mu partial p partial all over partial x times y square 2, okay, minus 1 over mu and all that. Finally, after simplifying the equation, this will be our final expression. Well, they are both, this equation is the general equation for the regional velocity, okay? This is a general regional velocity profile equation. Thank you.